Hi everybody, my name's Brad from KX Group. I'm here today to talk about a completely different topic to everything that we've spoken about before, and I'm here with my business partner Rajani. For anyone who doesn't know us, KX Group is the provider of multivariate data analysis solutions and deployment platforms into PAT systems. We've probably got about combined in our company 75 years plus of hands-on PAT application, from starting off with Pfizer with Phil when I was working in Pfizer in 2002, and right through to today, looking at different data solutions. So today the talk is centered on, okay, we've got all this hardware, we've got these processes. What do we do with the data? And lucky, and I'm talking about going back to 2002 when we were first implementing some of our PAT solutions. There was very little networking in a company. Your hard drive space was probably about 256 gigabytes, and that was if you had a procurement department that wanted to spend the money. And so we were learning everything from scratch. Today, we've got it really good. We've got databases, we've got fast instruments. I'm talking about spectrometers that we went from, I'll give you an example, when we went from going from 60 seconds per spectrum to 30 seconds per spectrum. That was brilliant. That was fast. Okay, and then all of a sudden the new instruments come out, the Zeiss Corona comes out. Oh, we can collect spectrum every 10 seconds. Oh, but we can fry an egg on the instrument as well because it used to get that hot. Okay, tumble blending. This is the machine that goes ping. Everybody loves their tumble blender. Okay, you talk to anybody in pharmaceutical industry. Oh, can we put an NI into a tumble blender? Yep, I remember the very first instruments that come out. They made no contact with the Wi-Fi, and so you lose all your batch data. There was no way to back it up. Okay, I've seen quite a lot of stuff over the years, but this talk is mainly about we're generating this data. What do we do with it? How do we use it? How do we use it to make our processes and our products better? So in any pharmaceutical environment, you've got the manufacturing and the quality networks, okay, and never trouble to talk to each other, because manufacturing can never influence quality, and quality can never influence manufacturing. And therefore we have two different networks completely isolated from each other. Oh, we can't cross that. Oh, that's terrible. So we call that the strict separation or the demarcation point. Okay. Now, when we go into a PAT implementation, we have to have that same mentality, because we're now bringing quality decisions down onto the manufacturing floor. And we do that through the use of this magic thing called PAT. Okay. So I was, well, a few of us here worked with before the guidance come out. And so we were making the rules as we were going. And then the magic guidance come out and we thought, yes, this is going to accelerate everything. But because the pharmaceutical industry moves as slow as slower than tectonic plates, okay, I got on the iceberg and drifted somewhere and hoped that I'd land, somewhere over time. But things are starting to improve. But you've seen this application many times today over the last 2 days. Excellent application, mainly. And one thing that hasn't been brought up in terms of sampling, this is 100% statistically representative sample that you're measuring, because it's the equivalent of a spinning riffler, which has got an RSD of less than 0.2%. That's why when we make measurements on the feed frame, they're representative of what the tablets are going to be. Therefore, we can put our diversion systems in and make good quality decisions. But I've seen it many times. You go into a factory, and then there comes to this, we just want to stick the probe into the side of the vessel and get measurements. And you say, no, you can't do that. Yeah, but there's so many publications out there that tell me I can do it. Yes, but we can publish anything. And I remember during my PhD, just publish it, because in 5 years' time, someone's going to prove you wrong. Okay, so we've got to really test what we're actually doing. But Okay, so now we've got NIR, we've got Ramen. Ramen was the poor cousin of NIR for many years. You know, like it was during the day, everybody was using an NIR, like the Big Foss. I don't know, does anybody remember the Big Foss XDS in the refrigerated cabinet? Hey, and if you just rocked it like that, you'd Spectrum would go. It's true. I was at a conference with Brooker once, and and the FOSS guys asked me to present, and the FOSS guys go, look, what happens when you measure with a Brooker system and you rock the table, and I said, that's your system, that's not theirs. Okay, so and we've had the wonderful opportunity to work on the last system. This one here is at the laser. What have I done?
That's the V.
Oh, that's the so where's the laser? Where's the point? I don't want to blind anybody.
The middle.
In the middle. Oh, there we go. This here, that's the entire manufacturing system. Size of a kitchen table. The additive manufacturing. You make the tablets in the blister packet. The little magnetic pucks go around. Each one of these has got a PAT associated with it. We can measure the quality of the tablets as they're being built. Slower than a tablet press, but faster overall. You've slowed the process down to speed the process up. With a bit of a paradox, but it actually does work. Because every time you build your blister packet, goes out. It's already packaged. It's gone out already. Okay, so PAT is about bringing quality into manufacturing. It's not about bringing the QC to the process. Okay, that's a big misconception. That was what we were drilled into when we were in Pfizer right back from the beginning. And it's about quality by design, not quality by testing. We don't put these systems in place so that we can test to death to try and test quality into our products. We're trying to build quality into our products so that we can put things like stop sensors or other surrogates around the entire system that will give us real-time quality information. So straight from the CGMPs from the 21st century guidance of 2002, which is the precursor to the PAT platform. Okay. If we look at it as an IT architect, don't get excited, okay?
I am. Glory. Tie it to the chair.
Well, you had all your spectra. Now,
we're going to talk about data.
Come on.
All right. So in a manufacturing system, this is your central system. Your SCADA, DCS, the system that's doing all your process control, okay? And it's talking to things like your sampling interfaces, your manufacturing equipment, okay? But these sampling interfaces are critical to the process analytical technology. And this is where we say, don't stick the probe into the side of the process and hope for the best. Understand your sampling so that your data is good, so that when it talks back to your supervisory control system, it's making a real decision. Now, hopefully I don't need to teach that, like that's already known in this room. Okay. Your PAT quality data management system, that's where we come in. Okay. That's the modeling, the advanced process control decision, or the decisions that feed down into that system. And that system says, okay, here's my result. I need to do something. And then in real time, you can see whether your change has made a real effect or it's made the process worse. And then we can take an action, a real-time proactive decision rather than a reactive decision. We've made 10,000 kilograms of powder. Whoops, there's a bad result. Let's just stick it into quarantine for 3 or 4 weeks and decide what we're going to do with it. Okay. Again, here's that demarcation point, the demarcation between quality and manufacturing. Okay. And then everything else, you've got your ERPs, your laboratory systems up here. We want to be able to take exact data from here, send it up into a database, link it up to a LIMS system, marry the two pieces of data together, model it, make the models, push them back down, and utilize them. The whole point is utilization. A model on a computer that's not being used as a pretty picture. Sometimes it's an ugly picture, but all depends on how we do. So just a little bit of a overview of how everything comes together. We've been doing this for quite a while now, but we're moving now into digital twins. The ability to take the information from your PAT systems, and then utilize that data even further, take the process information, work out what the predicted temperature of your mixing is going to be to understand what its impact is going to be on the stability of the API, etc. I'm not going to harp on this too much. But no matter what PAT we use, the data must be reliable. No, okay. Well,
I just took a picture, but I did not have the sound.
I shouldn't be like, but hopefully I'm not preaching. I'm preaching to the converted. Companies like Centronic make great instruments. Okay? They've done it for years. Okay, but if you just put it randomly into a process, it's going to do its job, but it's not going to give you any indication of what's happening in your process unless we use something like a representative sampling system at the point that's critical to the process, so we can generate consistent data, reliable data. If we're dealing with steady state processes, the data should be consistent. If we're dealing with dynamic processes, the spectra should change. Okay, so that's where our data understanding comes through. And a lot of things that we forget to do is to work out what the optimal number of scans are in order to generate the minimum variability in your spectral data. Okay. Then dynamic systems, obviously, we're limited by a number of things. The speed of data collection, whether we want to look at unit doses, and that's going to look at how we time our systems. But we should do some sort of static measurements as well in the begin with to understand, okay, if we measure at this speed, what sort of variability are we generating with respect to a static sample? And that will help us to understand how to best optimize or calculate the number of coads that we're going to do in a continuous way to generate models that look like this. And then the theory of sampling, of which I have been flogged so many times over the years because I wrote a textbook with Kim Esbenson, and all I ever heard was theory of sampling, total analytical errors, total sampling error. So I'm one of those disciples. And the thing is, I've seen a lot of examples where this spread here is quite wide. And I can tell you 99% of the time it's sampling variability. Our goal is to take that TSE, the total sampling error, and the total analytical error, remove that total sample, that sampling error, so that what we've got remaining here is the total analytical error. Okay? Now, we're never going to get perfection because nothing's perfect, but the more we can minimize that, the better we can rely on the models or the data that's being generated. It comes back to representative sampling. Now, recently, this guidance come out from the EMA. We already had data integrity as a theoretical exercise from the FDA, but the Europeans come out and spoke about the algorithm decision-making system. And when we read that paper, we'd already designed a product called Vector Vault, which is our data integrity version control system. And it was basically, we'd written a software product that met that guidance absolutely perfectly. Okay? And so I like to say this is going from the theory to practice. We're talking about the quality of data, but the quality of data is not the way it transfers from one hard drive to another over the internet. It's like in terms of being corrupted. That's one part of it. The quality of data is how you've collected it and utilized it to make a quality decision. And if we look at our what?
Rob, you okay? You need tissue?
Yeah, I missed it yesterday, that talk, but there is.
So if you look at big data in terms of a generic solution, what you see on the internet or like on websites, we're talking about volume, data capacity. Now, in the pharmaceutical industry, we generate small amounts of data compared to things like Netflix or the big marketing companies. But where they'll collect millions and millions of data points per minute in 3 or 4 rows, we collect thousands of points over variables. It has a massive impact on our computing ability. Okay? So rows, transactional data is really easy to process. And that's why these big data providers, that's all easy, But as soon as you go into thousands of variables, or in metabolomics, when you go to millions of variables, when you're trying to find metabolites in GCMS data, that's when your computer has to crunch for 3 or 4 hours just to generate one PC. And then if you find an outlier, you have to lift that outlier and do it again. And hope that your battery didn't run out. Or when I did my honours degree, we had a 33 megahertz computer, right, to run a PCA on 33 spectra, and they used to take overnight. That's an IGES system. You go click, and then you put a big sign on the computer, don't turn this off, and hope that the power didn't go off overnight. I can do that now in 10 seconds, okay? But that just shows you how things have changed over the years. But the one thing that we forgot is the verification of data, its reliability, integrity, completeness, consistency, timeliness, security, and availability. These are all the hallmarks of what we're trying to achieve in the pharmaceutical industry now in order to ensure that the data that we're using is good. So with that said, this is a must read. I had Kim gave me the honor of reviewing the text and looking at all of the corrections before it was released. I read it and I've gone, absolutely. I come out of the agriculture industry. I started off in IR for agriculture. If you think you've got difficult problems in pharmaceuticals, you haven't seen anything until you start working on agricultural calibration.
Yeah.
Okay, it is the most difficult, and that's why Pfizer at the time were looking for people like us who could look at really complex problems and help them with the with implementation in the pharmaceutical. But what we want to do is ensure that the data that goes into our models is absolutely of highest quality. Now, that leads you to your control strategy. How much time do I have?
4 minutes.
Oh, 40, did you say? The nice thing about you've got all this data, now you've got to put it together into a map, something that's going to make sense, something that's going to be a workflow that's utilized in process. And that's what we call a process map. So in this case, this is a continuous direct compression system with probably the mini batch blender as the focus right there. You've got your different feeders coming through your blender, and then the blender's talking to a sampling system. That sampling system has to make a decision. You've got your NIR in there. Does it go to the compression machine? Does it go to waste? Okay. Then you go to your compression machine, another sampling point, NIR on the feed frame. Do the tablets go to packaging or do they go to waste? Okay. So that's a very simple control strategy. They start from there and they grow to be much bigger and much more complex. So being able to drag and drop and make visual templates is really good. It's not only because it just helps you to better visualize what you're doing in terms of your control strategy. Okay. And one of the other things is your utilization of data. A number of years ago, I was asked about chemometrics, what the future is. And I said, PLS and PCA are never going to be superseded. Okay. Everything else is an attempt to find noise in data that, if PCA and PLS can't solve it, then you've got something that can't be solved in a lot of ways. But it's not the new algorithms, it's the utilization of the algorithms in clever ways to allow you to become more innovative. So if you look at a system like this, your data alignment system, you might have two sources of PAT operating on a single process point, or it could be PAT, temperature, pressure, different process variables. And we want to put the rejection algorithm. So Giovanna showed yesterday about how to use the spectral rejection algorithm to get rid of what's measuring the sampling system and only take through the data that's good. Now, you can take that through to a alignment point. This just aligns the data to a frequency that allows you to make a control decision in a timely manner, but before you lead to an out of specification situation. Okay? Well, you're minimizing that. Then you can then say, look, I don't need the entire spectra. I just need to extract the scores because the scores have got more information in it than the entire spectra. I could have prediction models here, and I might want to align that data to my values here. And then I apply the quality models at the end. So this model here might be a PCA model applied to the combined spectra and scores data. This model here might be just applied to that source there, and that model there might be just applied to those three scores that have been extracted. But we can do more with that. Then we can take a external calculator and take the outputs of models and generate new variables. Okay? So as long as you've got a canvas that makes you innovative, then it allows you to build really good controls situations. That's my first ever PAT implementation. Okay, old fluid bed dryer. This was a brand new. Sorry, Sebastian. This is right back in 2003. Okay? A brand new spectrometer called the FTNIR had just come out. Okay, and promised the world. So we got it in. We were allowed to pull apart our fluid bed dryer. So you can see here, this was a sliding mount. So we did all of our optimization on there. And then we built the system in the middle. And one of the things that I should note here is that here's your fiber optic probe. These are the design considerations. If that was to fall out of that box, it would never hit the ground. If the operators got bored during the night and they decided to use what's this probe, this little alarm here would go off and scare the absolute crap out of them. Okay. And then somebody would have to come in. 1 minute, yeah. Okay. And then here, this was our network computer box just behind it. Okay. With RAID 5, multiple storage systems. Okay. So overall, that was the control strategy. Connect up to your management system. I've put this in here just to show you an example. Do your modeling, put the logics back to a PLC, stop the system. Same thing with powder blending. Connect up the PAT, work out where the endpoint is, send the results back to a control algorithm, stop the process. You can do it for multiple batch operations. You can do it for continuous direct compression, where you've got the complete line coming down from blender to sampling system to tablet press, and additive manufacturing.